Good morning. Thank you all for joining us for the CXL Consortium Memory Challenges and CXL Solutions webinar. Today's webinar will be led by Chris Peterson, CXL Consortium Director and Hardware Systems Technologist for Facebook, and Prakash Chauhan, CXL Consortium Director and Systems Architect for Google. Now I will hand it off to Prakash to share today's agenda.
Good morning, everyone. This talk is about CXL, but I will start out the talk with the memory trends and challenges that are facing the industry. And this will be followed by some discussion on how emerging memory technologies can help with some of these challenges. At this point, I'll hand over to Chris, and he will discuss how CXL provides a great ecosystem to solve these memory problems. And he will also introduce CXL.mem flows that are required to support memory expansion devices. So this first slide, I want to highlight a trend that shows that memory costs have basically stagnated after scaling down nicely for a period of time. And so basically, cost per bit used to drop year over year, but starting about 2013 or so, the memory prices have flattened, and this causes an impact to system level cost because memory is an increasing fraction of system cost. And the demand for memory keeps increasing because the processor vendors increase the core counts to drive performance up. But the upshot of the memory costs staying flat and memory demand increasing is that system cost keeps scaling with the increased performance, and we end up with not so good performance per dollar. So next, I will sort of speculate on why memory cost per bit is not dropping anymore. And for that, I'll bring up the picture of how DRAM works. And basically, it is a charge storage device and a capacitor. And the capacitor stores charge that indicates whether it's a 1 or a 0. In the good old days when planar technology worked, we had the transistor and capacitor were both on the same plane. But as we scaled the technology to smaller and smaller dimensions, we still had to retain the capacitance value to store the charge. And that meant that the capacitor grew vertically. And today, it's like a tall, skinny structure. And if you look at the aspect ratios, they are kind of exceeding the 50:1 aspect ratio. To contrast that, the tallest building in the world has an aspect ratio of less than 10:1. So there are several problems with this current situation. One is that fabrication of this kind of tall structure is difficult and costly. Also, in order to keep the capacitance values stable, we have to increase the dielectric constants and materials that are used for dielectrics, and that makes the capacitors more leaky. So the net result of all this is that your transistors are leakier, your capacitor is leakier, things are crammed together a lot, so there's interference from cell to cell, from wires to cell, and so on. And that leads to variable retention time on these capacitors. And this is now resolved by using on-die ECC, which then adds even more area overhead. So essentially, DRAM scaling has become pretty difficult. So the next trend is that the memory bandwidth also needs to scale up as the CPU core counts increase. But over in the last 8 years or so, what we've seen is core counts have gone up by a factor of 3. However, the memory bandwidth for these systems has gone up only by 2x. What that means, and is shown in the red curve, is that the memory bandwidth per core is actually diminishing. And at the same time, we have applications and workloads that require more memory bandwidth per core. So we have a shortfall here. And the challenge is that to add memory bandwidth to a system, you have a couple of ways to do so. One is you add more channels to the CPU. What that does is, because each channel of DRAM requires hundreds of pins, it basically bloats the socket size. So now we have sockets in like 5,000 pins, 6,000 pins. And these kind of sockets are not only expensive to make, the contact reliability and all that also becomes quite hard to solve. Second issue with adding channels is that you have to route those channels, and that needs additional PCB layers, which is also a cost adder. The third thing is to accommodate all these DIMMs that you're adding because of the channel add, you have to figure out how many DIMMs you can place while still being able to fit in a standard rack width. The second way of increasing bandwidth is to increase the data rates, and we've seen that happen with DDR3, 4, 5. Each generation brings a faster speed bus. But this is not trivial. I mean, this is pretty hard. You have to do advanced PCB technology items such as backfilling vias, using surface mount and low pin capacitance connectors, and exotic via technologies in order to make sure that the signal is not distorted significantly. The other side of this increased data rate is that in a multi-socket system, you also have to scale the bandwidth between sockets so that the remote socket can get reasonable bandwidth to the remote memory. And that requires additional layers and low-loss materials to support. Also, in order to get data rates higher, more digital signal processing is required, which adds cost and complexity to both ends of the device and the controller. And finally, as data rates keep going higher, 2 DIMMs per channel is becoming increasingly difficult to support. And that brings its own issues in terms of how to support different size DIMMs to get the system capacity that you need. And you cannot have mixed DIMMs in a channel anymore because you only have one DIMM. So then the only way to get capacity is to go with exotic DIMM types like LR DIMMs or 3D stacked DIMMs. So this, we will kind of switch into emerging memories and what role they have to play in reducing the cost per bit aspect that we discussed in the earlier slides. So because DRAM is not scaling well, if we could substitute it with a different, cheaper memory, that could help us solve some of the system level cost problems. So this pyramid might be familiar to most of you. It shows faster and more expensive memory types towards the top, and cheaper but higher capacity and more persistent type of memories at the bottom of the pyramid. But the section that we're more interested in is the newly emerging memory types, which are slower than DRAM, but much more cost effective. And they are fast enough to be used in a load store model. And I've highlighted 2 tiers here because the nano RAM and magnetic RAMs are generally lower latency compared to the storage class memories that are resistive and phase change material based. So the other thing that's different about them is that their access times are more symmetric, whereas the ReRAM and phase change memory are more asymmetric read and write times. So we're trying to figure out how to fit these type of memories into our system memory hierarchy and lower the system cost. So one thing I wanted to kind of visit before we get into the integration into the system is why are emerging memories better positioned to scale beyond today? And to show that, I show like on the left, there is a memory array, and around it you have peripheral circuits like column and row decoders and sense amplifiers. And when we move to emerging memories, the way the memory is implemented is not on silicon, but based on the metal technology that we have today. So you essentially have word lines and bit lines that are orthogonal to each other, and the memory element is sandwiched between them. So they sit above the silicon layer, and the silicon can be used to implement the peripheral circuits. So that's step one. Step two is that you can, because these things are not the aspect ratio of DRAM, you can actually stack them on top of each other easily. So you get density increase by putting logic under the memory, and then you can stack multiple levels of memory. And finally, these technologies scale well with feature size. So you can go to a new lithographic technology and scale density that way. So they can keep growing in density for a while to come. Now, this is the question that I asked before, was how do you actually put this into our systems? And today, one approach is to have the emerging memory sit on a DRAM channel as a DIMM. But there are certain problems with this approach. One is that you might have to share that channel with a normal DRAM-based DIMM. And the other option is to put it on a channel by itself. But as we saw before, we want to keep to use all the bandwidth possible for DRAM, high-performance DRAM. So the general conclusion there is that you have to share this with another DRAM. But these new memories, especially like the phase change and resistive memories, are often transactional in nature in that they have non-deterministic timings because you might be doing some kind of wear leveling operation, or also they don't have the same read and write timings. So having the memory controller to support these two different media types becomes very problematic. So here we're talking about the kind of problems that occur if you try to solve this, to put different memory types on a DIMM type solution. So I already mentioned that we have transactional DIMMs that have problems coexisting with the regular DDR DIMMs because they lower the bus frequency in a 2D PC config, or you have to lose the channel bandwidth. Secondly, you have to arbitrate, the memory controller has to arbitrate between requests to DRAM and to the slow memory, and that impacts bus efficiency. And finally, you have interference between the DRAM and this new memory type, which causes the new memory type to steal bandwidth from your high-performance memory and increase latency. Also, in the current DRAM technology types, even if it was not transactional, we would have a problem because the memory controllers work best when you have the same generation of DDR. I mean, this is a file limitation actually because you cannot put a DDR4 and a DDR5 device on the same channel. Also, the speed grades and timing have to be exactly the same for controller implementation simplification. And the devices have to be the same geometry, otherwise you cannot interleave data across all channels uniformly, which is kind of important to get high bandwidth and low access times. Also, the DIMM form factor limits us in terms of what power and thermal headroom we have in putting different memory types. So at this point, I'll hand over to Chris to show how these problems are kind of helped by CXL, and take it from here, Chris.
Thank you, Prakash. So overall, CXL provides us with a number of opportunities to help address some of these challenges. So CXL is a memory agnostic and coherent interface. And in this context, when I say coherent, what I mean specifically is that we're able to map the underlying memory devices into the system address space so that we can do loads and stores directly to that memory device. The other area that this helps us address is really address some of the specific system challenges that Prakash walked us through earlier, and I'll get into more detail on how we can do that in just a minute. And then finally, CXL allows us to explore new and different compute and memory architectures because we now have the opportunity to separate out the memory controller or memory controllers from the CPUs themselves. So we can scale them independently. We can also build different types of heterogeneous compute platforms. So overall, CXL actually spans a wide range of possible use cases. For those of you who are perhaps less familiar with CXL, at this point we have 3 different device types defined: Type 1, Type 2, and Type 3. Specifically for this presentation today, we're going to focus primarily on what we call Type 3 devices. And these are basically memory buffers or memory expansion devices that allow us to provide memory bandwidth, memory capacity expansion, or access to other types of memories for system media and so on. So CXL provides us basically with a common standardized interface that allows us to put any number of different types of media or memory behind that interface. So now we have the opportunity to have a common platform interface with CXL, but then build CXL memory expander devices that have media-specific controllers. So for example, this provides us with the flexibility to support a variety of different memory devices. Those could be DDR3, DDR4, or DDR5 DRAMs. It could be low power DRAMs, or it could be persistent memory components like some of the ones that Prakash walked us through earlier. Or it could be some new media type that has yet to be defined or released into production. The benefit here is that now that you have a media-specific controller, you can address some of the specific challenges of those media types directly. So now you can have a specific controller for each type. So if there are asymmetric timings or non-deterministic timings, media-specific error handling mechanisms, or other needs that a particular type of memory requires, you can do that with these media-specific controllers. But with CXL, on the system side of the interface, we now have this common standardized interoperable interface. And you can design your platform such that you can create, basically provide common slots. And you can install any of these types of devices without having to worry about some of the details of the specific media, as it's a common interface. And then you can basically mix and match different device types from there. So overall, it provides us with a great degree of flexibility here so that for different use cases, we can apply the different media characteristics appropriately. So whether that's the persistence characteristics, different bandwidth latency characteristics, or even different endurance profiles, for example. So Prakash talked a little bit about some of the challenges with attaching different memory types in the same fashion on a DDR bus, for example. So ultimately, DIMMs themselves are not necessarily the ideal form factor for all of these combinations. And the way CXL helps us address some of this is that now we have the opportunity basically to isolate different tiers of memory from each other. So we don't have to share a bus anymore, and we can put the different memory types on a CXL interface, for example, which allows us to keep them completely separate from the direct attached DDR DIMMs that we typically use. The second benefit here is that this really allows us to scale up the memory bandwidth on a particular platform very efficiently, because we can simply scale memory bandwidth by scaling the number of CXL links that we provide on the platform. And this is a much simpler approach than trying to continue to scale DDR channels. It also provides a secondary benefit, because now we can do things like have one platform support direct attached DDR5, but also have DDR4 on the same platform for bandwidth expansion for specific use cases. And then finally, CXL really allows us here to continue to scale capacity as well. So similarly to bandwidth expansion, we can scale the CXL links up, and we can provide a large amount of additional memory capacity if the application demands it, just by scaling up the CXL links and the CXL memory devices attached to those links. So we're not going to be limited by the number of DIMMs per channel or even the number of ranks per channel, because we can scale those independently of the standard DDR channels. Ultimately, we also would expect that this should be a more cost-effective approach to scaling, because we can focus on optimized buffering solutions for CXL that don't have to rely on large parallel high-speed buses. So in terms of some of the other system challenges, so Prakash alluded to some of the challenges with the power and thermal limitations of DIMM envelopes. So typically, DIMMs have to be placed very close to the CPU. They're very tightly spaced because the electrical requirements are very stringent, especially as we go to higher speeds. And so that, as a side effect, really limits the power and thermal envelopes that we can do with a specific DIMM slot. And typically that's somewhere around 15 to 18 watts, and often even less than that in more dense platforms. That works okay for many DRAM applications, but in many cases, some of the emergent technologies really want to see a higher power envelope, especially to address some of the capacity challenges. And so we need a way to separate that out. And CXL enables us to do that, because now we can build basically a platform that has DIMM slots that is optimized for DDR DRAMs, for example, and then CXL memory slots, which perhaps could have a higher power envelope, 25 watts or more in many cases. And we can also optimize the cooling solutions for those particular types of devices versus trying to create a one-size-fits-all solution. And then the second challenge here that Prakash was talking about was just in general in terms of scaling the memory channels themselves. So a parallel DDR interface requires a little over 200 pins just for one channel, basically. Whereas with CXL, we only need about a quarter of that. So ultimately, that means we either end up with a lot less packages, less pins and signals per package or per socket, and we can build smaller sockets and smaller packages, or it allows us to pack a lot more potential channels into the same footprint as we have in the past. So if I look at that more closely, that definitely has PCB layer count implications. For example, just to give you a rough idea, a 6-channel motherboard today is on the order of 12 layers. As you move to 8 channels and up, you're a 16-layer motherboard, and from there, 10 plus channels are easily over 20 layers, which not only starts to become expensive, it also becomes a rather thick and challenging board to deal with. And that drives things like the back drilling and some of the other PCB technology improvements that have to be implemented that Prakash mentioned at the beginning. And then finally, because we're now talking about a serial interface with a much longer reach potential, you can also place the CXL memory in different locations. It no longer has to be sitting right next to the processor. You can put them in more optimal locations, which allow you to also optimize things like the airflow across these CXL memory devices. And that by itself will also drive the ability to support higher power, for example. So let's take a look at what a potential example solution could look like. So in this example, let's assume that we have a couple of different application requirements. In one case, we have the need for a relatively small amount of compute and therefore a relatively small amount of memory bandwidth or a relatively small amount of capacity footprint. On the other hand, we have an application that has very high core count requirements because it's very compute intensive, and therefore it also drives higher bandwidth requirements and higher capacity requirements. But in this example, what I'm showing here is that we have the potential now to create a common motherboard between these two applications. So what we can do on the left here is basically route out 4 standard DDR5 channels, for example, and that would be sufficient bandwidth and likely sufficient capacity for the lower compute use case. And then on the right, because there's higher core count, we can now expand the capacity and the memory bandwidth by adding 6 additional CXL links here. And those can connect to the additional either DRAM-based or other memory-based memory modules. And that allows us to scale up that capacity and bandwidth that I mentioned earlier. The benefit here, of course, is with this common motherboard, it'll be a lot lower layer count when compared to trying to route this with 10 DDR5 channels, for example. We're talking well over 800 less pins and signals that need to be routed, not only through the CPU package out through the socket, but also on the motherboard, of course. And so it should allow us to create a much more optimized motherboard and system solution here. And then finally, I can place those CXL memory modules in a more optimal location. And we can also dial in the memory bandwidth per gigabyte that makes sense for the application with those CXL memory modules, because now we can install not just DRAM components here, but also some of the persistent memory options, for example. And we can really mix and match as the application requires. So I'd like to spend the next couple of slides walking you through a little bit on some of the basics in terms of how the CXL Type 3 devices actually interface with the CPUs and some of the flows involved. So first, let's start real quick with a couple of basic pieces of terminology. In this spec, when we talk about these flows, we talk about a master and a subordinate. And in this context, the master is basically the CPU that sends the CXL commands, and then the subordinate is the Type 3 device or the CXL memory device. So let's start with a basic memory write flow. So the host or the CPU will send a mem write command. There are a couple of variants of this, but basically this is issued as a request with the data. And in some cases, this may include some metadata as well. This is a little bit less relevant in most cases for Type 3 devices, but applies to some of the other device types. And that metadata could be used for tracking coherency state, for example. So when the memory device receives that, the memory controller will send that out to the media itself as a write operation, typically with some ECC as well, and then include the metadata if it's available and if it's supported. Then the media device, if needed, will send back a completion to the memory controller. And then the CXL memory device will send the completion with no data response back to the host, saying that the write has completed. All right, so the next flow we will go through is the memory read flow. So it's similar here as well. So we send a request with no data in this case as a memory read. Sorry. There we go. Typically the metadata here is sent as a no-op, assuming it's supported. The CXL device memory controller will then send the read to the media. The media will respond with the data and ECC if applicable, in addition to the metadata. And then the response is sent back to the CPU as a response with data. And the metadata here is basically just any state, as it's not as applicable for the read flow. And then finally, there's also the case where we may have a memory invalidate that we need to issue. This is typically used in a couple of different cases, but one relevant example here is that it could be used to tell the device to flush its caches out to persistent media, for example. So the way this works is the CPU will send a memory invalidate command. Generally, that includes some metadata. In this context, uses the value of 0. The memory controller goes out and reads the media itself to determine what the current state is. The media will respond back with the data plus some ECC and the current value of that metadata. The CXL memory device will send a completion with no data back to the host. And this is just a completion. There's no additional data component here. And this will include the old value of the metadata. And then the CXL memory device will issue a write with its associated ECC and the new metadata value. And then finally, if needed, the memory device will send a completion back. So now that we've walked through the basics of the type 3 memory flows, I just want to come back to the storage pyramid that Prakash brought up at the beginning. So what I've explained here is that CXL offers us the opportunity to help provide an interface and a new attached solution that covers a big portion of this pyramid here. So everything from DRAM through the NRAM, MRAM, 3D crosspoint and phase change memories, most of the emerging technologies we expect we should be able to attach with CXL. Of course, this is just the beginning. There's quite a lot of work that has to happen here, as with any new interface. And there are a couple of specific areas that I think are worth highlighting here. Ultimately, we're going to need a lot of help from the industry and from a lot of the consortium members to make sure that what we build is truly a strong ecosystem and we address a lot of these challenges. So on the hardware side, for example, not only do we need to continue to grow the ecosystem itself, we need to go off and build a number of compatible devices. We need to work through the interoperability here. We have a pretty long, good track record of developing interoperability for PCI Express, and so we need to continue that here with CXL as well. So we've talked a fair amount today about form factors or some of the challenges with form factors. So there's clearly a lot of development and alignment work that has to happen there to help us work through some of the power, thermal, mechanical, and management interface pieces there so that we can build form factors that are suitable for some of these emerging applications. Then we also need to spend a lot more time evaluating and characterizing the memory latency characteristics here. We are going to be adding some amount of latency as you add a CXL interface. And so developing benchmarks and tooling around this to help us really dial in what the right characteristics and the right designs are is going to be very important. Finally, on the software side, we need to work through a number of challenges there as well. Because of the latency difference that I mentioned, we're going to have to think about non-uniform accesses to that memory. So we need to think about how do we schedule jobs that may take into account latency, bandwidth, or capacity characteristics. We need to think carefully about interleaving approaches to ensure we get the maximum parallelism we can do, but without ultimately impacting the aggregate performance. RAS here is going to be also an important topic. We need to think about how do we do unified error reporting and handling for these different heterogeneous memory types. How does that get exposed to the system? How do we log it? How do we respond to them, and so forth? Security is an important topic as well. We need to not only think about the security of firmware running on these devices, but also media security, so your data at rest solutions, because we may potentially have pluggable devices, for example, so we need to be concerned with some of the security challenges associated with that. And then different media devices will have different integrity and isolation challenges as well, and that also translates into quality of service effects that we need to look at. And we need to look at this at both the link and media level and understand the potential interactions there at the system level. So in summary, CXL allows us to build various memory tiering solutions with a variety of media types, including the different emerging technologies. And it allows us to do so in a media-independent fashion while addressing some of the scaling challenges, both from the media side as well as from the system side. And finally, it allows us to build a future memory roadmap here by providing us with new opportunities and new potential architectures so that we can continue to scale the memory capacity and bandwidth in the most efficient fashion for our future server generations. And with that, thank you. I will turn it over back to Elsa.
Thank you, Chris and Prakash, for sharing your expertise. We would like to encourage our viewers who's interested to learn more about CXL to join the CXL Consortium, download the evaluation copy of the CXL 1.1 specification, and engage with us on Twitter, LinkedIn, and YouTube. We will now begin the Q&A portion of the webinar. If any of our viewers have any questions, please submit via the BrightTalk chat window. We will start with the first question. Will CXL latency be similar as DIMMs connected directly to CPU?
Chris, do you want to take that?
Sure, I'll take a first shot at that and then feel free to jump in. As I alluded to earlier, there is going to be some amount of added latency here. You are moving from a CXL interface and having to translate that to some other media-specific interface. So there will be some amount of added latency. Having said that, CXL was designed from the ground up to focus on minimizing that latency as much as possible. So all of the layers in the CXL stack were designed for low latency. And so the focus will be to minimize that as much as possible.
Yeah, I think the goal was to have it look like a remote socket memory latency, if it is actually DDR that you're trying to attach to the CXL device. So it would be like a NIMM node that you typically see on a dual socket system.
Another question is it possible to interleave multiple CXL channels to improve CXL bandwidth usage?
So I'll take a first shot at this as well. So the interleaving mechanisms are really application specific and implementation specific. Having said that, there's nothing in the spec that precludes you from enabling interleaves across devices or even within the devices themselves. So it's really an implementation choice.
What is the purpose of meta value? Is it for cache coherency?
Sorry, Elsa, you broke up a bit there at the end. What was the question again?
The question is, what is the purpose of meta value? Is it for cache coherency?
Yes, that's correct. So that's the typical usage. So you can share the state of the line that way. So, you know, whether it's exclusive, shared, or any, for example, or depending on what your coherency protocol is, that's the intent, is to provide the state of that line.
Do you see a value for small capacity, low latency NVDIMM as a complement to CXL expanded memory, which will have a higher latency than DDR? This could be lower latency persistent memory such as MRAM, NRAM, or DRAM buffered small amount of PCM RAM on NVDIMM.
Okay, I'll take this one. So yeah, I mean, the point of CXL is to provide options. So you can still continue to do innovative stuff on your DDR channels, but you have to be careful that this other memory that you're attaching does not affect the bandwidth and latency aspects of the DRAM that you have, because then your system starts seeing hiccups. And also, you don't want to lose bandwidth for your DRAM, so you have to basically see how whether your DRAM controller can handle like different timings and still be able to meet the high performance, high efficiency, high bandwidth, low latency characteristics.
What is the expected relative latency to CXL attached memory compared to DDR attached memory?
So
I think we already covered that. Go ahead, sorry.
Right. Yeah, exactly. So I think Prakash answered this really well earlier. I mean, obviously the exact number will vary based on specific implementations, right? But as Prakash alluded to, it could be on the order of you know, a second socket NUMA node latency.
What is the granularity of the mRead, mWrite number of bytes cache line OS page?
Yeah, so it's the CXL.mem portion is cache line based, right? So all of these are reads and writes of your cache line granularity.
Does CXL support atomics? Can a processor issue, compare, and exchange type atomics ops over CXL?
Chris, I'm not sure if I know the exact answer to this, but I assume that you should be able to these kind of operations.
Yeah, I mean, you just have to think of it as loads and stores to memory, right? So it's not anything special outside of that. You don't need any special operations like you might have to do with I/O atomics.
Are we enforcing app developers to change the application to support CXL-based memory?
So CXL memory is just added to the system address space. So depending on what you want to implement, it could be fully transparent to applications. Of course, that is an implementation or a system or a platform choice. You could also make the choice to expose it as different regions, for example, different NUMA regions, similar to the way we do things with multiple CPU sockets today.
Yeah, I think if you want to get the most out of it, you might, if you want to get the most out of your system, you would have to probably consider the different tiers and do things accordingly. But if you are not very worried about, if you just want additional capacity and bandwidth, and you can deal with different latency and characteristics for different memory addresses, then you can make it completely transparent.
Why do we need the meta value and the metadata for Type 3 devices?
So those are optional fields, so you don't necessarily have to implement them. It's a choice. There might be some use cases that would still want to use those if you want some degree of coherency engine still within the device, but they're not required.
Do you expect memory device directly interface CXL?
I mean, it's not forbidden.
Yeah, go ahead, Prakash. Yeah, I think that's an implementation choice, right?
But I mean, the general understanding I have is that you want to keep the memory and the media controller separate, but one could integrate everything in one device.
Will latency time crossing the PCIe bus be reduced? Thinking about low latency requirements in HPC or HFT.
I'm not sure if the question is about PCIe or CXL. For CXL, by making the flits and having different channels to send those flits over, you can achieve low latency. But PCIe is not the topic that we're discussing here, so I'm not sure whether the question meant CXL or something else.
Does a CXL write command specify a column row address, or does the media controller assign the location in the media?
Yeah, so columns and row addresses are media-specific definitions. So that is handled typically by the media controller or the memory controller itself.
A compromised endpoint shipped with a rootkit will mean access to the entire or most of the SAM. How do we mitigate these challenges?
So I think in general, security of platforms, regardless of the interface, is a very large and deeply discussed topic in the industry today. And there are a number of solutions that are in flight to help address this. And CXL will follow industry best practices, as well as some of the other improvements being implemented in other standards.
Is there any difference of meta value meaning between Type 2 and Type 3 devices?
No, I mean, the CXL.mem commands are the same. Whether it's a Type 2 or Type 3 device, it's just a different implementation, and in some cases a different response if necessary.
So in slide 6, it shows an independent memory channel on CXL. Is that an expected channel count choice amongst platform vendors? What is the expected size of each memory module over CXL?
So I think we will probably not be talking about specific product and platform offerings. You can basically have to talk to your processor vendors to find out what they're planning to offer.
Any thought on CXL link efficiency, for example, actual data rate versus physical link bandwidth?
So I've seen some estimates. It obviously depends on how well your traffic packs into the various CXL flip types. But if you were to compare with a PCIe DMA kind of application, your efficiency is lower than what you get on PCIe because this is cache line size transfers. So for bulk transfers, your efficiencies can be in the 70–80% range. And that's okay because the data rates start at 32 gig transfers per second. Chris, do you have additional insight?
Yeah, I think that's a good estimate at this point. To Prakash's point, though, it is going to be workload dependent, right? And also to some degree implementation dependent in terms of what specific optimizations might be implemented. So I think we will know better as devices start coming out on the market.
I assume if the system mixes and matches, say, DDR5 and DDR4 over CXL, for example, that would create non-uniform latency and non-uniform bandwidth, right? Total bandwidth scales, but if it would create software work to account for difference in bandwidth and latency between different memory types.
Yeah, so if you want uniform interleaving across uniform memory types, then that is indeed true. And you have we have to do the work.
Yeah, I mean, I would just add that I think that's the case even today, right? If you have a 2-socket server, you already have non-uniform latency, non-uniform bandwidth access anyway, because unless you pin your software threads to a specific socket, you already have to solve this problem.
For a Type 3 device, can they ignore the metadata since they are meant for cache line space?
Yeah, I think I answered this earlier. It's an optional for Type 3 devices.
How does the host initially determine the latency and bandwidth of given CXL attached memory?
I believe this is through this is provided through ACPI tables as and if it's exposed as a NUMA node.
Yeah, that's correct.
What are interleaving options accounted for CXL memory for fit rate or RAS consideration? For example, modules becoming unavailable due to uncorrectable. Does the entire CXL channel become unavailable?
Yeah, I mean, the exact choices around how to do interleaving at the system level are really going to be processor and implementation specific in terms of your goals around RAS or bandwidth and so forth. The spec doesn't actually provide any limitations here. It really depends on what makes sense for your specific platform.
Do you see CXL as a first step towards moving second-tier memory out of the box entirely?
So that's an implementation-specific question, and while it is possible, and as Chris mentioned, due to power and thermal considerations, it might actually be beneficial. It's not mandatory or, yeah, I mean, moving outside the box has its own challenges, like cabling and keeping synchronization between of power and other stuff between the two boxes. So I would not necessarily say it's moving second-tier memory out of the box, but it definitely opens the possibility if your system architecture can deal with it.
In the context of keeping memory costs low for the system, how much memory does a CXL module need to accommodate to make up for the added cost of the controller that will be required between the CPU and media?
Yeah, I think that's a good question. You have to do the math and figure out how it works out. Basically, what percentage of your memory can be slow, and if that percentage is replaced by this additional controller plus the new memory type, what cost does it work out to?
Is ECC required to be transported over CXL.mem?
So I think it depends on what ECC is meant in this context. But if we're talking about media-specific ECC here, no, it does not get transferred. I mean, cache lines themselves don't. It's just a data cache line. You're not sending ECC with it. So if it's media-specific ECC, the memory controller handles that, and that's just a transaction between the media controller and the media itself. CXL as a link has multiple layers of protection built into the link itself, similar to PCI Express. So the link itself is protected as well.
So this question is about the CXL Type 2 device. How can an accelerator on the CXL endpoint comply with the host memory consistency model?
I think that's probably, yeah, go ahead, Prakash, sorry.
I was just going to say it's not directly relevant to this particular presentation, and I would direct them to the CXL spec.
Okay, this will be the last question. Can two sockets which are not connected via a coherent interconnect use the CXL metadata meta value to manage coherence for CXL connected memories?
So that's not really the intent here. CXL supports asymmetric coherence protocols, and you need to still have a coherency agent on the CPU itself. So the memory device itself is not intended to be a coherency agent.
So being mindful of the time, we will wrap up today's webinar. The presentation recording will be available on CXL Consortium's YouTube channel, and we will upload the slides on CXL's website. Unfortunately, we couldn't address all the questions we received today, so we will be addressing them in a future blog, so please follow us on social media for updates. Once again, we would like to thank all of you for attending CXL Consortium's Memory Challenges and CXL Solutions webinar.